this next bit belongs, it's found in chapter 2, but it sort of belongs in chapter 1 because it's another graphical method of displaying the data in a distribution. Specifically, we're going to be dealing with a distribution which is numerical, but continuous, not discrete. In other words, if 3 is a value in the distribution and 4 is a value that someone could get in the distribution, 3.1, 3.074, whatever, all of those are possible values. Let me give you an example. Height, human height. I say I'm 4'8", but I'm not exactly 4'8". There's like basically nobody who's exactly 4'8". Given that there's an infinite number of possible heights between, so did I say 4'8"? Ha, yeah, I'm 4'8". Given that there's an infinite number of possible actual heights between 5'8" and 5'9", there's probably no one who is exactly 5'8", and if they're exactly 5'8" in 1 second, they're not exactly 5'8" the next second as they grow or lose hair or something like get a haircut. So density curves are a way of displaying these distributions, which are a lot more common than people generally think. Let's take human height of 18-year-old men. We could display them in a histogram, where over here you have people between 5'0" and 5'2", and over here you have a bar, and it's a pretty small bar because there aren't that many people, and then you have between 5'2" and 5'4", you have a significantly bigger bar, and then between 5'4" and I'm running out of space here. I should have done this a little more tightly. Between 5'4" and 5'6", you have significantly more people. And between 5'6" and 5'8", you have, really quite a sizable chunk of the population between 5. Yeah, this is a histogram, right? You have all these, you have all these bars that represent how likely things are to happen, and maybe over here on the left you have an X that says % of population, and up here you have maybe 30% of the population are in this bar, and so forth. The issue is that one issue with histograms like this is that they don't really tell us where inside the bar each person is. Wouldn't it be handier if we had smaller bars? Yeah, so this bar would be small at first, for the first half of it, from 5'0" to 5'1", but then 5'1" to 5'2" would be a taller bar. 5'2" to 5'3" is significantly shorter, and 5'3" to 5'4" is significantly taller. More detail, right? More detail is good. And so forth. Not so many people 5'5", but then significantly more than that, people who are 5'6", 5'5", 5'6", and so forth. By getting narrower bars, you get more detail. And you could do this again. You could split them into half bars again, and get more detail, and so forth and so forth. The question is, what happens if you continue this to its logical conclusion, until you have infinitely thin bars? How many people are exactly 5'0", or like nobody? How many people are exactly 5.1? No, well, you have very thin, very short bars. Of course, you can decrease this measure. Up here, instead of 30%, you're going to have up here you have 1%. And infinitely thin bars is a bit much. But what I'm going to draw is going to have infinitely thin bars in theory. You know what? No. That's not even true. Right, this is referred to as a density curve, and density curves have obvious features. For one thing, you're never going to have a negative percentage. So this line is never going to go below 0. But more relevantly, the total area under this curve, and anybody who's taken calculus, their eyes are, their mind's going off like alarm bells. The total area over here is 1, because 1 stands for 100%. 100% of everybody is under this. And so if I wanted to ask the question, how many people are between 5, 10, and 6 feet tall, I would take a look at this wedge and measure the area of that wedge. And if the area of that wedge came out as 0.1642, I would say 16.42% of people are between 5, 10, and 6 feet. And you're probably wondering who could ever know enough about a population to build a density curve. And to some extent, you're right, this isn't handy, right? If you only have 5,000 people that you have measured, you're not going to be talking about what's in between. But let's say you have a theoretically infinite population, like the world population, all right? And you've figured out about how often everything happens. You would sometimes use a density curve to describe what you think the world population is like. You would say, based on the data we've gathered, we believe that the shape of the distribution of human heights looks like this. You would develop an equation that you think describes humanity, and then you would, draw that curve, and boom, you'd be able to measure subsections of it. And the reason I describe the human population as infinite is not only because it's so many billions of people that you're not even going to measure 1% of it, it's also because we keep generating new people, and those new people would have values somewhere in here. So here's how this could really be used. You say, a random person is about to be born. How tall will they be at age 18? What's the chance that a random kid is going to be between 5, 10, and 6 feet? And you would say, 16.42% chance that a random baby will be somewhere between those two heights. Now, density curves are generally used then not for specific data that has been gathered, not for statistics purposes, not as a measure of what we gathered, but as a way to explain what we think the broader population is like, the theoretical population. And there's one particular density curve that you're going to see a lot of, and that is the normal distribution. And the graph is sometimes referred to as a bell curve or a normal curve. But it is a perfectly symmetrical distribution which shows up an awful lot for something that is purely theory. People built this equation, they're like, wow, all sorts of stuff fits into this, into these, results. It constantly happens that the mean is exactly where the median is, and that if you go, it's basically shaped like this. There's a few extremes at either end. Most everybody is about, a lot of people are about 5'9", but there's plenty of people that are 3 inches shorter or 3 inches taller. But if you get 8 inches taller, 8 inches shorter, there's very few people. And then every so often you get a really exceptional person at either end, but it's extremely rare. The normal distribution goes on forever in both directions. And we're going to do a lot of calculations involving it. Let me fill in a few things. There are certain things you're expected to memorize about the normal distribution. First of all, since it's symmetrical, the mean is exactly where the median is. The mean result is the 50th percentile. 50% of everybody will have a negative z-score, 50% of everybody in such a distribution would have a positive z-score. And then on top of that, if you go 1 standard deviation in each direction, %68 of data points in a normal distribution will have z-scores somewhere between positive 1 and negative 1. They'll be somewhere between 1 standard deviation above and 1 standard deviation below the average. Let's take a look at the IQ test, for example. In the IQ test, they've designed the IQ test so that the average result will be 100, and the standard deviation will be 15. Notice I'm using Greek letters because we're talking in general about populations here, not about samples. They've tried to adjust it so that the average will be 100 and that the standard deviation will be 15. And that way they will be able to say, oh, you got a z-score of 100, and you got a, you did 1 standard deviation above the average, we will score you 115 will be your IQ. So what does that mean? That means that somebody with an IQ of 130, if you've had your IQ test and you've been measured as 130, you are 2 standard deviations above the mean. Your z-score would be 2. And as for your percentile, we'll get to that in a bit. Let's first measure the percentile for people who are 1 standard deviation above the mean. So I've mentioned that 68% of everybody is somewhere between a z-score of -1 and +1 on a normal distribution. That means that this area contains 34% of the population. This zone contains 34% of the population. So let's say somebody has an IQ score of 115. How well did you do? How many people did better than you? Well, there are 50% of everybody is below the mean, and then another 34% over here, so you did better than this many percent of people. If you got an IQ test and you got 115 on it, then they are saying that you are smarter than 84% of the population. How about 2 standard deviations above the mean? Well, if you go 2 standard deviations in each direction, this is the second thing, these are all amounts you should memorize, sort of like trigonometry where you're supposed to memorize root 2 over 2 and all that stuff. For the normal curve, you're expected to memorize what percentage are between any 2 locations. And we'll get to the table in class. 95% of all people are between 2 standard deviations above and 2 standard deviations below the mean. So if you have an IQ score of 70, then that means that you have a z-score of -2 because you are 2 standard deviations below the mean. And what percentage of people got higher scores than you? Well, 95% of people got between here and here. That leaves 5% that are outside. And of those 5%, half of those are below you. So if you got a z-score, if you got a IQ score of 70, then you are smarter, or you scored higher than, theoretically, 2.5% of all people would score if they all took IQ tests. And they also expect you to memorize 3 standard deviations from the mean, and how many percent of people are inside that. Once you go out that far, I mean, if a typical person has exactly average intelligence, and the typical distance from that people are is 15 points, how often is it that you find somebody who is not just smarter than the average, but if the average person smarter than the average is here, they are 3 times as much smarter than the average person smarter than the average? That's extremely rare. How rare? Well, 99.7% of all people are within 3 of all data points in a population are within 3 standard deviations of the mean if the distribution is a normal distribution. And as we have been seeing, or will be seeing tomorrow, the normal distribution is a very common feature. I want to say it shows up in all sorts of places where you wouldn't necessarily expect it. And that's why we're bothering with it. Like, the math of the normal distribution has been worked out, and it just keeps showing up in theory in situations where, in theory, we should be getting a normal distribution. So it's considered important to know how it works. Yeah, you could go to the Museum of Science and see it create itself time and time again. We'll see it created in the data we gathered also. And then we'll talk about why that happens, more like chapter 7. So, you're sometimes going to be asked to calculate your way between a variety of things. You'll be given a mean and standard deviation and a z-score, and be asked to calculate the actual result. So for example, I could say the average IQ is 100 and the standard deviation is 15. Jill got a z-score of 2.15. She said, I'm 2.15 standard deviations better than the average, smarter than the average person. Okay, what did she score on her IQ test? Well, then you would say if the z-score is 2.15, the formula for z-score is result minus average over standard deviation, and you would calculate back up, multiply by 15, add 100, oh, her score was blah. Or you could say, well, add 15, add another 15, she's at 130, and then add 15% of 15, which is 2 point whatever, she's 132 point something. That's, she probably got 132 on her IQ test, unless they're doing decimals now, which I don't think they do. Yes, or you could be asked to go about it the other way. You could be given really any three things in that formula and asked to find the other. Or you could be told this person got a score of blah, calculate their z-score. You could be given a percentile and be asked to figure out what their z-score is. And for that, you will have, both in the back of your book and on your formula sheet, a table that is there to tell you the percentiles for all possible z-scores in a normal distribution. Let me find it here. It should also be on your formula sheets. Here it's on page T1 and T2. They have a whole bunch of percentiles. So let's say Jill said, I got a z-score of 2.15. Okay, how exceptional is that? What percentile is that? And they have a table here where you can go to 0.7, 2.0, 2.1, and then move over to 2.11, 2.12, 2.13, 2.15. 2.15 has the z-score 2.15 has a percentile, the probability of being somewhere to the left of that, the probability that a randomly selected person is to the left of that. In other words, the percentile that person is at is, what is it? There it is, 0.9842. And that means that Jill with a z-score of 2.15 has a percentile of 0.9842. 98.42% of people she meets, if she meets totally random people, will have IQ scores lower than hers. Yeah, so that is, and there are theoretical reasons that intelligence specifically, among other things, should fit into the normal curve situation, should be measurable in a normal curve, and that's why they create the IQ test so that it will be measured, in a normal distribution, so that you'll be able to refer to everybody's place in the normal distribution, refer to the place among their peers as a normal distribution. And we'll talk about that in class. I plan on it anyway. Ask me about it if I don't. Yeah, the normal distribution. There it is. Oh, let's do one more thing. Let's say I wanted to know what percentage of people can be expected to score between 130 on the IQ test, and 140. So that's between a z-score of 2 to a z-score of 2.67. Well, I can figure that out using this table pretty easily. I'll find 2.0, the percentile here is 97, the 97th percentile. The percentile for 2.67 is 0.9962, unless my eyes just deceived me. No, they didn't. Good. So what percentage of people have IQs somewhere between 130 and 140? This minus that. That's the percentage to the left of this minus that. What's this minus that? Just that little area. So that would be 0.0962 minus 0.0772, 0.19. So apparently about 1.9% apparently 1.9% of all people taking the IQ test will have scored somewhere between 130 and 140. That is, people who will either round up to 140 on the IQ test or round down to 130, but not actually be either of those things, because nobody, theoretically, the normal distribution would score exactly 130 or exactly 140. It's all rounded to the nearest number, because it's a continuous distribution, like height, where nobody is exactly average or exactly anything, exactly 5'1". Nobody's going to have an exact IQ score that's going to be measured precisely to the number. It's all going to be rounded. Yeah, there we go. That'll do.